Hello everyone, welcome to my YouTube channel. Today I am going to explain transformation in 2D and 3D, in which we will cover the topics scaling, rotation and translation, and we'll do the matrices representation of it. So first question is, what is transformation? So transformation is basically changes the position, size and orientation of the objects and used in computer graphics to manipulate 2D and 3D shapes. There are three basic types, which is scaling, rotation and translation, and can be combined using composite transformation matrices. So we'll come to next, translation. In translation, so basically translation means moving an object from one position to another. So we'll write x dash by x plus dx, t is translation, y dash by y plus dy, and p dash by p plus t, and p is the position. To find the position of the object and to find the translation, we'll use the x dash and y dash. So matrix form of this is p dash is equals to p into t. We'll come to the next, which is rotation. Rotation is basically when we go from y-axis to x-axis and x-axis to y-axis. So we'll write in cos theta and sin theta form. काउंटर क्लॉकवाइज रोटेशन होता है इसमें. सो विल राइट एक्स डैश इज इक्वल्स टू एक्स कॉस थीटा माइनस वाई साइन थीटा एंड वाई डैश इज इक्वल्स टू एक्स साइन थीटा प्लस वाई कॉस थीटा. मैट्रिक्स फॉर्म में हम लिखेंगे काउंटर क्लॉकवाइज को. कॉस थीटा माइनस साइन थीटा 0, साइन थीटा कॉस थीटा 0 and 0 0 1. Now we'll come to scaling. Scaling means changing the size of an object. So we'll write it as x dash is equals to x into sx and y dash is equals to y into xy. So we'll अगर हम इसका बेसिक फॉर्म पढ़ लेते हैं, so it will benefit us in future questions. Now its matrix form is sx00 and 0x sy 0. So we'll write in diagonal form ss, sx, sy and 1. Now we'll come to 2D homogeneous coordinates. Matrix representation in homogeneous form will be x dash y dash 1 is equals to xy1 into transformation matrix. We'll find a 2D homogeneous coordinates. Using homogeneous coordinates allow all transformation to be represented as matrix multiplication. Okay. Now we'll come to reflection. Reflection about x-axis is 1 0 0. We'll also write in diagonal form 1 minus 1 1, and in y-axis minus 1 will be in top, 1 and 1. Now we'll come to composite transformation. In composite transformation, combines multiple transformation into one matrices. For example, translate, rotate, and then scale. Now composite matrix can be written as Cm is equals to T into R into X, which means translation into rotation into scaling. Okay. Now orders matters in this because different orders give different results. Now we'll come to rotation about a point. So basically it includes some steps, which is translate point to origin. First we have to go to the origin, and then we'll apply the rotation, and that will come back to the translation process to back into its original position. So we'll write as Cm is equals to Txr yr into r theta into t minus xr minus yr. We usually write translation in positive, but we have putting the object into the origin, then applying it, we are translating it the point to origin, then applying rotation, then translate back to original position. So we are coming back. So we will put the minus in the translation. Now we'll come to the 3D scaling. Matrix form will be when we see in previous PPT, there's a 2D scaling. We'll write in a diagonal form. So we have to do the same here, but we'll take SZ in it. So we'll write X, SX, SY, SZ, and 1. Scale object in X and Y and Z directions independently. Now we'll come to 3D rotation in Z axis. So rotation about Z axis, we'll write the equation which we put in the matrix form. Then we'll write the 1 in the second index and in the last index. Now we'll see the x-axis and y-axis 3D rotation. In x-axis, we'll write the 1 in the 0th index and then the equation. Then the last in the last line, we'll write the in the last index 1. Then we'll come to y-axis. First equation, then we put the 1 in the 1th index and then equation, then when we put 1 in the last index of the list. Then we'll come to the 3D reflection. In xy plane, z becomes negative. In yz plane, x becomes negative, and xz plane, y becomes negative. So identity matrix with one diagonal element as -1 will take. Okay. Now, what is window to viewport? Window is basically our laptop. Window is an area in world coordinate to display. Viewport is a area on display device where window is mapped. So using scaling and translation process in it, formula involves xw max, xw min, yw max, yw min, and viewport dimensions. Okay. Normalization transformation includes some steps in which we translate window from lower left corner to origin, then scale to viewport size and translate to viewport position, in which it involves negative because we are coming back to its original position after scaling it. So its formula is transformation is equals to T x v min. V is viewport, y v min into s into t, in which will minus the, because we are coming to the window, we are going to the viewport, so we take first v, then in last we take w, minus xw min minus yw min. Then we'll come to the key points of it. So transformation basically includes translation, rotation, scaling, and reflection. And matrices enables combining multiple transformations. Order of transformation matters.